Well, thank you so much for that introduction, and of course you can ask me more about the Gamer project over dinner. But I'm also a backscatter skeptic, so this work also will go in towards that direction. So to get started, we all know these predictions of millions and billions of IoT devices in the near future. And most of them currently have a battery, right? This is not really sustainable. Most of the times these things are glued in and are hard to remove and replace, and then often the entire device, when it doesn't get properly recycled, ends up in the landfill. This is not really a direction we want to head. So the research on intermittent computing tries to solve this issue. So replacing the battery with just harvested energy alone. But if you remove the battery, this execution will become intermittent. You will have cycles of charging and discharging of your device. But we have a solution for this. We save the state and restore the state of the system with checkpoints and restoring it. So the field has been working towards different frameworks to checkpoint the system to save the state. There's now a long list. Maybe you were on the keynote on Monday, but this it gets more and more difficult to gain more, to really make a breakthrough here to make it more efficient. So you see the field expanding into different directions, such as platforms, and of course backscatter communication has always been a big part of intermittent computing. However, backscatter still requires this signal source, this common thing that needs to be present in the room. And this is still quite a big burden for people to have in their house, for example. All the solutions of networking of these battery-free intermittent devices are currently only broadcasting based, so they're not bidirectional, capable of communicating bidirectionally. And of course you want to update the firmware of your devices, so this is not really a great solution either. If you deploy thousands of these sensors, you need to go across them all to manually update the firmware. So essentially the problem, what we want to solve is you have this connection with your device, right? And how can you deal with the problem of when not enough energy is available? Can you basically resume the state of such a network connection, right? You don't want to be reconnecting all the time with your smartwatch, for example. So in our vision, you would at least need to be able to save and restore the state of the system. And this includes the network. You also need to be able to recover connections if you had a power failure unexpectedly. If the connection is still within the time period that allows for recovery, so it has not dropped entirely, then why not resume the connection? And also, of course, you need to adapt to the available energy you have. And this actually introduces a unique point that isn't really talked about in intermittent systems before, is that with these communication protocols, such as Bluetooth, you need to communicate at a very accurate point in time. Microseconds, more or less, can mean that you skip a packet or not communicate and the whole chain falls down entirely. So visually, our proposed solution would look something like this. We add checkpoints to the system, and when you experience a power failure and then recover, then you would instantly seamlessly resume and not be able to reconnect. And this also has the additional benefit that our system is able to actually switch off when idle instead of going to sleep mode. And we found that this saves considerable amount of power. So bear with me here. I know it's a big slide, but we propose a new kind of architecture to make this happen. And this centers around two power domains. So one, ultra low power with only a tiny RTC to be able to keep track of time. and the other power domain basically with the processor and any sensors you have. And then this tiny RTC is able to switch on and off the power to the system. So we are able to turn on the Bluetooth controller, the microcontroller, when we want to. So we do not require a sleep mode. To make this come together, we have a whole bag of tricks. I will go over some of them today. And one thing is the process-based checkpointing, which we introduced. I will go over a little bit later. But one crucial thing is this deterministic restoration. Because if the restoration process of the device is too long, then you might exceed actually the scheduled packet that you want to intercept, that you want to react to. And again, this connection, it needs to adapt to it needs to adapt to the available energy. So you want to communicate slower when less energy is present, and you can communicate faster when enough energy is present. And the final thing I want to mention is by virtualizing the bottom layers of the systems, like the interaction with these core embedded peripherals, such as timers. If we virtualize those, we can make the system think that it is continually operating in time. And this allowed us to run basic, a full Bluetooth stack using this architecture. So more about checkpointing. Of course, after the introduction on Monday, you've heard all about intermittent computing. But there are basically three types of checkpointing so far. You have task-based systems that introduce a set of computation in terms of energy that you can autonomously execute. And if you exceed this, then you would have a perpetual cycle of not being able to make any forward progress. You have the software-based approach where you just insert a checkpoint at a certain point. This is also difficult, right? Because with a Bluetooth stack that can be hundreds of thousands of lines of code, where do you put a checkpoint? We argue that this is also not the best approach. And finally, hardware-based approaches usually check if a capacitor voltage has been reached, and then they will start checkpointing. But this could actually interfere with networking itself. You might prioritize the need to have this communication over the final checkpoint. So to solve these issues, and of course the fact that to transition a thing like a Bluetooth stack of hundreds of thousands of lines of code into task-based architecture will be a long time of work. Maybe Apple, Microsoft could do it, but for us that would not be feasible. We introduce a actually very simple process. We use actually the linker to separate the memory of three different categories in our system. So we have the applications, we have the network, and we have the OS. And just by dragging and dropping the files into the respective folders, we are able to separate the memory and only restore the memory that we require, right? Because if you're only doing some sensor sampling in your application, you don't need the whole network stack to be restored. So this is a method how we achieve further efficiency with our system. And we, of course, double buffer this in memory so that it's incorruptible. So our system looks a little bit like this when it operates. So traditionally, we start from power off instead of usual standby. And then we determine what we want to restore at runtime. So we want to restore the OS or the network depending on what you require in that specific power cycle. And then we have the synchronization step. So we synchronize with the external RTC. And if this succeeds, so that we have woken up at the point in time we expected, we proceed normal execution. So at this point, the scheduler will start and operation is resumed as normal. If this doesn't occur, if a timeout occurs on this synchronization, we actually recover the connection, any potential connection. We try to look if this connection timeout has not occurred. And if it is possible to recover, then we'll propagate the network state forward. Additionally, we're able to dynamically restore applications for when, for example, a network task has triggered an application to execute, so you don't need to go through the loop again. And finally, when all execution has finished, actually the scheduler is able to determine when would be a sufficient point, a suitable point in time to checkpoint the system and to switch off. So in a different, on a timeline, it looks a little bit like this. You start up, you restore what you require, in this case a network cycle. So we restore the network, the operating system, which is also responsible for the inter-process communication. The synchronization occurs, then this packet is exchanged, and again the checkpointing cycle starts if nothing else is scheduled for that point in time. So we view our architecture as generic, but we of course had to pick something to demonstrate. And in this case, for us, it was Bluetooth as a protocol that we chose. And we made this hardware platform called Freebie, which integrates these components into one tiny board. And so this is a combination of like a Bluetooth module, this external RTC, and an energy harvester with some supercapacitors. So what we really wanted to achieve is compatibility with all kinds of Bluetooth devices, right? Because the strength of Bluetooth is the compatibility. So first, I would like to show a simple connection. So we connected to a smartphone, and here we compare our Bluetooth implementation against the stack. The software stack is based on called Packetcraft. And here you can see our system actually switching on and off often. That is why there's this huge inverse current on the bottom left. But our system is more energy efficient. It remains active even though the other system dies and is unable to recover the connection. On the right side, you can actually see this connection recovery in action. On the bottom, we've indicated the packets going back and forth. And you can see that the system, the storage voltage dies when we turn the power supply off. And when we turn the power supply back on, the system resumes the connection if nothing happened. And this is not, again, I want to stress, a reconnection, but this is resuming the already pre-existing connection. And for IoT devices with slow communication intervals, reconnecting with Bluetooth also means re-exchanging of a lot of packets, of connection configuration, of all these types of packets. So this can be up to 60 seconds, or for complex applications even more. So we've also made a kind of simple smartwatch that is able to show time as a demonstrator. It also shows email notifications if you connect with your phone to it. So it was a fun demo for us to demonstrate the capabilities of our system. And we've evaluated at different light levels, so 300, 600, and 10K. And here we also show that if you have more energy available, our system is able to communicate more often. So here I also really want to stress, it is not any custom Android kernel or anything. There's just a normal Android phone. It just works. And also, it enables firmware updates, right? You don't want to go around with these hundreds of thousands of sensors and manually update the firmware. So this bi-directional communication that really enables these devices to be implemented in the real world. So our main strength of our work is power consumption, because when we're able to switch the system off, like the microcontroller off, and keep this RTC on, we don't basically have any standby power. So only nanoamp type levels of just the RTC. And here we reduced, so we are really more efficient than even like the state-of-the-art Bluetooth stacks from the manufacturer itself, not the open source variant where we worked with. So this implementation could also save power on battery-powered devices, because usually the implementation of a Bluetooth chip is actually separate to the main microcontroller. It runs on like a Cortex M0 next to the other as a companion chip. So in these types of chip architectures, you're actually able to switch off the Bluetooth chip with the existing infrastructure that already exists by just applying these state-saving tricks. And here in the figure on the bottom left, we show that compared to Packetcraft, the original stack we used, the open source stack, we are actually more efficient at 4 seconds already. However, at longer intervals, this grows. Finally, if we look at like the proprietary stacks, the thing that really kills our efficiency is the use of external memory to store our state. So if we deduct this overhead, we're actually able to beat the proprietary network stack in terms of power consumption. So that was a fun thing. So wrapping up, we introduced a new kind of architecture for the future of battery-free devices. This is a little bit orthogonal to backscatter, which requires the infrastructure. We can run this anywhere, right? We can just throw these sensors on a wall, anywhere. And also the range is far greater because you don't need to reflect the signal back. And this approach, since we only change the bottom layers of the code and save the state of the system in a simple way, we maintain compatibility with all the devices that exist basically with Bluetooth. So we also introduced a new efficient checkpointing method that's really simple to use and is able to incorporate these large code bases into existing applications, incorporate code bases of existing applications, and we are able to recover connections. And finally, as I mentioned, we're able to save power compared to even battery-powered solutions at long connection intervals.